Hello everyone and welcome back to an L582 Modeling and Control of Electronic Machines and Drives. Well, the last lecture we ended talking about three-phase induction motor, and that actually concludes the main important machines we tried to cover in this course, starting with the C machines. They were just our principles to start talking about machines, and then that took us to the major two machines, the synchronous machines, and especially in its generator mode, which is the typical generator for all power plants or most of the power plants you'll be dealing with, and the three-phase induction motor, which is the workhorse of industry, and the motor which you pretty much will see it in any industrial facility you may be encountering. So for this lecture and the coming two lectures, we will be talking about other what we call special machines, which is machines that are not that popular like the other two kind of big machines, but you will be seeing them around, and that's a good idea just to have a quick overview about them. I think we already have a very solid ground from the previous machines, and now we understand what's about the machine and how the energy conversion happens and how the torque is produced and all that stuff. And we had a lot of principles covered in the all over the semester, so I think just talking about a very quick overview about those machines will give us a lot of information about them based on the previous principles we have already covered. Okay, so I'm gonna talk today about single phase induction motor. Okay, from its name, it's just an induction motor, but single phase rather than to be three phase like the three phase induction motor we talked about over the half semester almost. Okay, so for this kind of a machine, I'm gonna say that it is mostly used for small and residential applications. Okay, as it requires just single phase source, not three phase. Okay, and the single phase source is actually available everywhere. Okay, so yeah, it's on our home and in any kind of facility you'll have just single phase power all the time. Three-phase power, on the other side, most of the time it just happens with industrial facilities, so you'll not find them that common in the residential, commercial, and small industrial facilities. So for those, we like to go with just motors that require to be dealt with single phase. So it's just a sort of a plug-and-play motor. Okay, you don't need to have a specific three-phase source to deal with, like the three-phase induction motor, but just you need just an outlet, a normal outlet as you can find in your home. Okay, and that's why it's a bit popular in the single phase induction motor, because yeah, it's just available. Okay guys, so whenever you find a single phase source, and actually you can find it anywhere, you can just plug in this motor and it will work. Okay, so that's how, or just why we use this, or why we actually bothered of having this kind of a motor. Okay, about the construction of it, we'll not be talking a lot because it is the same stator and rotor of squirrel cage induction motor, our three-phase induction motor. Yeah, so it's just like the square cage induction motor we deal with all the time with three-phase induction motor. Okay, but it's mostly square cage, not wound rotor. So it's the same stator and rotor we dealt with before with the three-phase induction motor. Nothing to say here, but the stator and rotor winding are single phase, not three-phase. Okay, so you're using almost the same kind of a stator and rotor we dealt with before with the square cage induction motor, but we just use a single phase winding, not three-phase winding. Okay? And how this will just affect the performance of the motor actually. Because if it's just that easy, why from the first place we just went to three-phase? If it's just that easy, we can just use single phase and the motor would work just fine, and that's pretty good. Why we bothered actually to go with the three-phase stuff and the need for three-phase voltage source and all that stuff? That's why we will jump to talk about the theory of operation. Okay, so like we said, the stator of such machine will just have the same shape like we had before with the induction motor, but now we're dealing about just having single phase. Okay, so we'll be just having one set of winding. Okay, so the current goes here inside those wires. That's current going from here and coming out from this side. Okay, so it's just here, like I say, just one winding. That means they are all connected in series. Okay, so you're talking about one winding. That means set of coils connected all in series most of the time. Okay, so you're dealing with here, so the current goes from here and coming out from there using the right hand rule like we just did before. That will give you magnetic field going into this direction. That means there's a north pole here and a south pole there. Okay guys, but what is the difference between this and the three-phase induction motor? The whole point is, while a three-phase winding fed from three-phase supply create a rotating magnetic field, a single phase winding fed from a single phase supply creates a pulsating magnetic field. That is the major difference, and it's actually a very big difference. For a three-phase machine, a three-phase winding fed from a three-phase supply, it will create a rotating magnetic field, and that's very good because it can actually create torque and just will drag the rotor to rotate with it. Okay, if we're talking about single-phase machine, which we're talking about here, it creates a pulsating magnetic field, not a rotating magnetic field. What I mean by this pulsating magnetic field and why it's not good. Okay, so keep that in mind. Rotating magnetic field creates torque as it pulls the rotor to rotate behind it. Okay, that's the rotating magnetic field of the three-phase induction motor. Remember, like we said, in the three-phase induction motor, we just have a poles north, south, north, south, and those are rotating around the circumference of the machine by the synchronous speed. And because of that, your rotor body, which is here, which will also have its own magnetic poles, south, north, south, north, those will be magnetically coupled to the poles of the stator and rotate with them. And that's the whole point of how this machine can work. So the machine will have a starting torque higher than 0, and that means the machine is self-starting. Like we said before about three-phase induction motor, the machine can start from its own. Okay? But if you talk about here for a single phase machine, why do we say it's pulsating magnetic field? What we mean by pulsating magnetic field is, like we said here, it's just, if we look at the stator and look at what we have as a winding here, it is just one winding, have two halves like you see in here. This guy will be just creating here, like in here, just a north pole here and a south pole here. The whole point is it does not rotate. Why? Because you just have a coil. It's just this guy will be just equivalent to, you have a coil like that and it is connected to a single phase supply. You have a current going here and this will create a magnetic field here, and that's what we need. But what about how this magnetic field looks like? Let me just have a look here. That is the current versus time, okay? And this current maybe will be a sinusoidal wave like this, okay? It's not perfect, but yeah. To look at the magnetic field that will be produced from this, I will also look sinusoidal like that, okay? It will also just change with the change in the current, because the magnetic field depends on the current that's just moving inside this winding. Okay, guys? Or these coils, whatever it is. So the whole point is, with the change in the current, it just begins from 0 here to the flux is just 0. The current goes here, positive, so the flux goes positive. Positive, maybe just you have a north pole here and a south pole down there. Okay? And the current keeps going up, and that means the strength of this magnetic field goes up. Yeah, it is still north pole, but it's just going up with it. With the current going down again until it's 0, the flux strength goes down back to 0. And while the current goes down here to negative, the flux goes to negative with it. That means the north turns to be south and the south turns to be north. And it's also changing value here because the current keeps changing value. So the strength of this magnetic field keeps changing. You know what I mean? So what will happen is this north pole and this south pole will remain at their position. They will not rotating anywhere. They are just changing value. You know what I mean? So sometimes this north is the north, sometimes it is south. It depends on the current direction. And the current keeps changing direction because it's AC. And this south pole sometimes south, sometimes is north. And even its value is not fixed. The value, the strength of the magnetic field keeps changing because the current, its value keeps changing with time because it's sinusoidal. So the magnetic field just changing with time. All this happens, but those poles holds position. They does not rotate anywhere. So that's the whole point of this. Pulsating magnetic field means poles, magnetic poles, changing strength and polarity. Sometimes it's north, sometimes it's south, but fixed in position. They does not rotate around the circumference of the machine like as a rotating magnetic field. And that's a big problem because this will not create torque. Okay? If you remember, with three-phase machines, because the poles are rotating, they just drag the rotor to rotate with them, and that's how the machine actually rotates, because that's what you need from the motor to start rotating. But from here, you just have poles fixed in position and changing magnitude. That's why we call it pulsating. It keeps pulsating in just value, strength. But they does not rotate. They fixed in position. They keep in their position. And that's a problem. That will not create torque. Okay? So this does not create torque. So the single phase induction motor is not self-starting. That means this machine will not start rotating from its own because its magnetic field from the kind of pulsating, not rotating like the three-phase induction machine, and that's why it's not self-starting. Okay, guys? So the whole point is we need starting methods to make the starting torque T starting higher than 0, so the machine will start rotating, because now we'll have a starting torque. Okay guys, I hope you got the idea now. You just have one single phase winding fit from a single phase supply, so it's pretty much equivalent to this. It's just a coil fit from a single phase AC supply. So the current goes here is sinusoidal, and this will make your flux sinusoidal. That means it's changing value with time and changing polarity with time. Sometimes it's positive, sometimes it's negative, means sometimes north, sometimes south, and it keeps changing value. But the whole point is it's stationary in position, it does not rotate. Okay? And the rotation around the machine was the only thing that makes three-phase induction machine, or just the three-phase winding, is very popular, because you have from just a stationary winding, you created a rotating magnetic field, and this rotation is what we need, because it will just force the rotor to rotate with it, and that's how you create torque. But while having here, it's fixed in position and keep pulsating in its place, it will not create torque, and we need to find something else to deal with this. Okay guys? Okay. So if you are trying to mathematically present this problem of the pulsating MMF and how it will just impact our performance, I'm gonna go and try to represent what we call the Magneto motive force, okay, MMF. We abbreviate it as just F. What is this Magneto motive force? It is just the force that pushes the magnetic field into its path. Okay, it is so much analogous to the EMF, the electromotive force, which is the voltage difference in electric circuits. Well, the voltage difference in electric circuits is the force that pushes the electric current to move into the wires. The magnetomotive force is the force that pushes the magnetic field to just move in its path, okay, inside your machine, for example. Okay, how to calculate it or how to derive it, it's not our just main concern actually, but it will take this form. F will take just F as a magnitude sine omega et, which is the frequency, time, multiplied by sine P over 2, which is the number of poles, multiplied by theta mechanical. Okay, this P is the number of poles. That is the mechanical angle. So as you see, it just depends on both on time and on position, on the mechanical angle or mechanical position. Okay, because it's different around the machine here to just develop how much magnetomotive force will be just about here. Okay, so it's different with time, because with each time here you have different amount of current, and the higher the current, the higher this magnetomotive force, because it's in turn gives you higher magnetic field, you know. Okay, so it depends on the time, because the time, with different time you have different magnetic fields and different currents, because it's sinusoidal excitation. Yes, and it's different on position, because if you just look on this position here, for this position maybe and this position, so in this point and this point you will have high magnetic fields, because that's where the position of the poles is. There's a north pole here, or the south pole, and here the north pole or the south pole. But in different positions here around, so maybe in this point up or down here you don't have magnetic field, so you just, the magnetic field here almost equals 0. You know what I mean? That's why it's just different. That's why if you represent the magnetomotive force, it will have just to be depending on both time and position, time and theta. Okay guys, if you do the math of this, because we have two signs multiplied together, it will just give you this form: F as a magnitude over 2 cosine P over 2, the number of poles, theta mechanical minus omega et, that is minus f over 2 cosine p over 2 theta mechanical plus omega et. That is the representation of the pulsating MMF. Okay, so that is F, which is the pulsating MMF. It has two parts, as you can see here. So this part, guys, it is just the representation of the rotating MMF, the one we have before in three-phase and induction motor. Okay, guys? But you see here, the pulsation, it just has two of them with a very big problem. One here has a negative sign, one here has a positive sign. That means that the pulsating MMF is equivalent to two sets of rotating MMFs, but rotating in opposite directions. So if you want to represent the MMF, the pulsating MMF, that will be just like that. If you have in here an MMF just rotating with the synchronous speed in this way, and another one rotating and also the synchronous speed but in opposite way. So the resultant speed of them will be just 0. So that is why the pulsating MMF has 0 speed. It does not rotate. That's why we call it pulsating, because just it keeps pulsating, it keeps changing value and polarity, but in its position it does not leave its position. Okay, that's why we can just have them represented like that. The summation of two rotating MMFs, but one negative and one positive. That means one rotating clockwise and one rotating anti-clockwise. So the resultant of them will have 0 speed, does not rotate at all. Okay, guys? That's why I'm saying like that. The F pulsating will equal F forward plus F backward. So you have a summation of forward and backward. One just going forward. I'm gonna just say that the one goes clockwise, we call it the forward MMF, and the one goes anti-clockwise is the backward one. Okay, while those equals here, those guys are just equal. Sorry, no, it's not negative. Yeah, this one is negative. Okay, from here, yeah, so yeah, that's negative here. So that's the whole point. F forward equals F backward, which is the case here actually. So that means F pulsating will have 0 speed. It will not rotate anywhere, just will keep pulsating in its position. Okay, guys? And that's why the starting torque of the motor will equal 0. The motor will not have any starting torque unless we do something to just tackle this problem. Okay, guys? So that's the whole point of having just a single phase winding fit from a single phase supply. It's a problem. The motor will not just create torque, it will refuse to start. And that's why this kind of motor is not that popular at three-phase induction motor. Three-phase induction motor, you just need to have a three-phase supply, plug the motor, and it will start rotating instantly. But with a single-phase induction motor, yeah, it's good because you can use it with a single-phase supply, which is just available everywhere. But this motor is not that good because, like we're saying, it will refuse to start from its own. That's why we need to go further and investigate how to start it. So I'm gonna say here starting of single phase induction motor. That's the very important step. Okay, how to make it starting, how to make it is starting torque higher than 0. Okay, so guys, the main idea is to use an auxiliary winding shifted by 90 degrees from the main winding and feed it by a current with 90-degree phase difference compared to main current, and this will create rotating magnetic field like three-phase induction motor, and this will make your starting torque higher than 0. It's that obvious. The whole point is, in our motor we just have a single phase winding, so we just have one winding like that. The current goes in here and comes out from there, and that's just the main winding. And this main winding, like we said, will create a pulsating magnetic field. But what will happen if you just add another winding? So we just don't have one winding, another winding here. Okay guys, just have another winding, the current goes here, comes out from there. Now we have this to be auxiliary winding. Okay, but keep in mind, both main and auxiliary windings are connected in parallel to the same single phase supply. Okay, because it's just one supply, it is a single phase supply. We will not have different two supplies to just have a supply for each winding. We will not do this, okay? Because like we said, we will not sacrifice the advantage of this motor. We just came all this way to this kind of a machine because we want to just use this with a single phase supply. So the whole point, we will not just get two phase supply or something, with just supply will have two phases with a phase difference between them just to do this, because likewise it will, again, a special supply, you will not find it everywhere. So the whole point is, do whatever you want, but keep in mind we are just using a single phase supply. It is just this one. So we're going to use an auxiliary winding but connected in parallel with the main winding to the same supply. Okay guys, the whole point is, like you've seen here, this guy has an axis like that, and this has an axis like that, and that's a 90 degree. So they look like balanced two-phase winding. Remember we just had before with the three-phase winding, remember? The three-phase winding will just, if you remember, look like that. We just have three-phase winding, that's a phase, and that's a phase, and that's the third phase, yeah? And we just said that is the axis of this one, that is the axis of that one, and that is the axis of this one. And between every one and the other, let me make it more obvious for you. Yeah, so this one has an axis like that, and the other one has an axis like that, and the third one has an axis that's 120 degrees, 120 degrees, 120 degrees. That was balanced three-phase supply, but it's not uniquely for three-phase winding. Actually, you can use whatever number of winding you want, but make them evenly distributed around the 360 degrees, and now they are balanced. So we dealt with three-phase winding, three-phase system, because that is the most commonly used one, but it's not dedicated to it. So if you use five-phase fit from five-phase supply, it will create also rotating magnetic field. If you use two-phase, which two-phase supply will create a rotating magnetic field. It's the same principle, but we just deal with three-phase because three-phase is the most commonly used type. Okay, guys? So the whole point is, if you can create balanced set of winding, whatever the number of winding is, 3 winding, 4 winding, 5 winding, whatever it is. So here we just use 2 winding perpendicular to each other, and now they are balanced. So those guys are balanced two-phase winding. If you can feed those from 2 currents, okay, so if we can feed the balanced two-phase winding by 2 currents with 90 degrees phase difference, that means they are balanced two-phase currents. So the same like the 120 degree phase difference back in the three-phase currents with the three-phase system. Now you have a rotating magnetic field, and that's what we are looking for. So that's the main idea, guys. Don't use just one winding, use 2 winding perpendicular to each other. That means a 90 degrees phase between them, and now they are like 2 phase winding balanced. And try to do anything to have the current in the main winding and the current in the auxiliary winding has 90 degree phase shift between them, and now you have a rotating magnetic field just like the 3-phase winding used with 3-phase induction motor. So that's the main idea. We'll be just trying to play around here, and it has different shapes to deal with. Okay, guys? So let me take you here with those different starting methods for the single-phase induction motor here. Okay. The first method of starting of single-phase induction motor, we call it the split-phase motor. Okay. How this method works? Oh, let me grab you the photo for the schematic diagram of this one. Okay. This one should be. No. Okay. This one. Yeah. What is this? That's a schematic diagram of how you just connecting the 2 windings. So remember, we have 2 winding all the time, so that's the main winding, and that's the auxiliary winding, and they're connected in parallel like you see in here. Like we said, they're connected in parallel like that, and here is your supply. Okay, that is the single phase supply we are using. Okay, that is the supply. Okay, guys, so you just have yeah, that is the rotor obviously, and the 2 windings are used on the stator. I don't need to say that. Yeah. Okay, so you're just using an auxiliary winding, so that is all the time, that is we talking about the stator here. Okay, the rotor is just a square cage. We don't have any access to the rotor, if you remember. Okay, so the rotor here is square cage, which is just bars closed together as short circuits, and that's it. But here we're talking about the stator. The stator has 2 sets of winding rather than just 1 single phase winding. We have 2 phase winding here. So we have 2 winding, the main winding and auxiliary winding, and they're connected in parallel to the same supply. Okay, so how this works, we use an auxiliary winding or let's say with thinner wires than those of the main winding. Okay, this makes the impedance of auxiliary winding different from impedance of main winding, and this creates phase difference between the main and auxiliary currents. So like we said, we can use two winding in parallel, but the whole point is they cannot be identical, because if you have just two identical winding connected in parallel, they will have identical currents, and we don't know this because even there's two winding and just have 90 degrees phase shift between them in space, so they are balanced winding, they will not create a rotating magnetic field unless the currents moving inside them has also a phase shift, 90 degrees phase shift. Okay guys, so we cannot make the two winding identical because the two currents will be identical and that will blow everything. So this current I main and this current I auxiliary has to be having different phase shifts, having different phases, different angles. How we do this? By making sure that is those two winding have different impedances, different Z auxiliary and Z main has to be different, so the angle of the main current and the auxiliary winding will be different. Actually, we need this angle to be 90 degrees, but for this case, it will not be 90 degrees. But before jumping into this, let's talk about here. This is a switch. Okay? So this is mechanical or mechanically operated switch. It senses the speed, and once it reaches steady state speed, it opens. So actually this auxiliary winding will not be there all the time, it will just be there for the starting, and this switch here senses the speed of the machine, and once it already started and the machine just passed the starting period and reached steady state, it will just open, and this will hold this auxiliary winding out, and you just keep going with the main winding, and that's it. Okay, so all happen here. The whole point is now the main and auxiliary windings have different wire sizes, so their impedances are different. Okay, so I main, which equals V over Z main, and I auxiliary, which equals V over Z auxiliary. Like you've seen here, those two currents will have some phase difference. Okay, and this will create torque. Why? The whole point is that we want the phase difference between those two currents to be 90 degrees, so they will be just balanced. But like that, they will not be 90 degrees. So this phase difference here will not equal 90 degrees as we want. Okay? Because we cannot create that. So we just have two winding and we'll just make them different in cross sections. So that will just create different impedances and have different angles for the current. But they will not be purely 90 degrees as we want. Okay? So they have some phase difference, but not the desired 90 degrees. Once the theta is just 90 degrees, that means just the MMF will not be purely rotating. Rather, there will be also two rotating fields opposite to each other, but one of them is higher. So remember, when you talked about this, that is the pulsating MMF we're talking about here, having two components, one forward and one backward. Yes? So if you have this, if the angle theta equals 90 degrees, this backward field will equal 0. It will go away entirely, and F pulsating will be just F forward, and that's totally rotating, just like three-phase induction machine. Okay, guys? But because here the theta is not entirely 90, it's not 90 degrees, there is some difference, but it's not 90 degrees. So yeah, this backward magnetomotive force will not go away entirely, will not be 0. But the whole point is, for this, if theta does not equal 90 degrees, but also theta does not equal 0, and that's the case we are dealing with here, we created some phase difference. Yeah, it's not 90, but it's not 0 either. For this, F forward will be higher than F backward. Okay, guys? So the two F's, one forward and one backward, will not be equal, so they just cancel out. No, for here, one of them will be higher than the other, and that means we'll have some resultant magnetomotive force. Okay, guys? So F forward higher than F backward, so the motor creates torque and starts rotating. Okay, guys? But keep in mind, but F backward will keep acting like a brake, and this reduces torque. Okay? It will just like all the time that we have F here forward, and that is what we need, and we wish that F backward goes away entirely. But the whole point is you will have some F backward here all the time. But because this F forward is higher than F backward, it will just have the resultant of them will be just going in favor for the F forward, and the motor will start following this forward magnetomotive force and will just rotate. But this F backward will just keep all the time acting like a brake on this motor, so it will not create that much of a torque after all. Okay, guys? To keep in mind also, that's what we're saying, because auxiliary winding has thinner wires, they must be disconnected after starting, otherwise it will overheat. Okay, because the thinner wires will not withstand the same amount of current that can just go in the wider wires and the main winding, and that's why we just disconnect it. We don't leave it there, we just leave it for the starting, and this switch after this opens and just disconnects auxiliary winding, otherwise it will burn down. It's not designed to this, it's just designed to make you pass the starting period. That's it. Okay guys, so if you want to look at the torque speed characteristics of such a motor, it will look like that. Okay, so that is the torque speed characteristics of the split phase single phase induction motor. That is, yeah, split phase motor. That is torque speed characteristics of both the running and starting characteristics. Okay, so look at the running one, which is the red characteristics, like here. That's a regular torque speed characteristics, but the whole point is, look here, the starting torque equal 0. That means you're just using the running winding. If you use just the running winding, it will look like this. I'll not have any starting torque and the motor will refuse to start. And that's why we use the auxiliary winding for starting, and that's why the actual torque speed characteristics is the black one, what we call it the starting characteristics here. Now you have a little bit of starting torque. It's higher than 0, and that means the machine will start rotating. So what will happen is your motor will be just following this torque speed characteristics here, the black one, until the switch just opens. Once the switch opens here, you're now going to just jump to deal or just keep working on the red one, which is just using the main winding. So this one, the red one, is just using the main winding only. This black one, which is the starting characteristics, main plus auxiliary windings. Okay guys, so you start on the black one using both of them until you just pass the starting period and the switch opens, and just get out the auxiliary winding out of the circuit, and thus you just, now we just working with just the main winding only, so we jump to work on the other characteristics. But once we reach here, we don't need the starting torque anymore because the motor has already started rotating, and yeah, its inertia will keep the F forward higher than the F backward. After disconnecting the auxiliary winding, the motor inertia will keep F forward higher than F backward, and that's why the motor keeps rotating. Okay guys, again, what are the pros and cons here of this method? So the pros here, it is very simple and cheap. You just need another winding, that's it. But the cons, which should be obvious from here, it is small starting torque, because if backward does not equal 0 and acts like a brake. Okay, guys? So the whole point is you use this if you're just dealing with a small load. Okay? So that means it's just suitable only for light loads. Because like I said, we didn't cancel the backward magnetomotive force entirely. It will be there all the time, like you see in here. Okay, our goal is to just keep F forward alone. Like that, it will act like a three-phase induction motor, almost. But this F backward is here all the time because of this design. The angle between the current in the main and auxiliary winding is not 90 degrees because we cannot do it like that. We can just change the angles by changing the design of the winding, by making it thinner a little bit. But this will not create a 90 degrees phase difference between the two currents, and that's why we are not cancelling the backward force entirely as we are aiming for. But yeah, it will create some torque. It's good enough if you're talking about a light load. And those light loads most of the time are fan loads. Okay, so if it's just a small fan, you want to just have a small single phase motor to work with. So this kind of a motor is good enough. Okay, guys? That was the first method to use. Just use an auxiliary winding with thinner cross-sectional area and use a mechanical switch with it to switch it out. Okay, switch it off, sorry, after you pass the starting period. It's good enough for the light loads on smaller motors. So if your application like that, it does not require that much of a torque to start with. So this method will be good and cheap enough to go with. But if it requires higher starting torque than this, so this method will not work, and we need to go with a better method, which having higher starting torque, and this is what we'll be talking about the next lecture. So yeah, thanks so much guys for joining me today. Take some time to review the lecture before we jump more to talking about other starting methods the next lecture. Thanks so much for joining me today, and I hope to see you all next time.